Today we're going to go ahead and finish up section 5.1, talking about the fundamental identities of trigonometry. Yesterday we focused on Pythagorean identities, and I wanted to run something by you that I realized last night when I was thinking about it. You know, I was trying to get you to be used to hunting for Pythagorean identities. What that means is you should always be on the lookout for squared trigonometry, because all of the Pythagorean identities have squared trigonometry in them. So when we were doing this first example in the notes, I guess what I should have said that I didn't say is that I had to square both sides. That had to be the first step, because all 6 of those purple Pythagorean identities involve squared trigonometry. So when you see squared trigonometry and pluses and minuses of 1s, you're thinking Pythagorean identities, always on the lookout for them. And today we're going to use some identities to try to simplify some more stuff. Then we're going to use some identities to do some really neat trig solving, equation solving. What am I trying to say? Trig equation solving. There we go. I'll get the order of those words right eventually. I told you when we're going to be doing trig proofs, which we will begin doing in the next lesson, that I don't always know how to start a question. I don't always know exactly what path I should be taking. But through experience, I do know certain tricks that work, or certain paths that are usually going to be what we're looking for. Here I have a fraction. Actually, 2 fractions with addition or subtraction between them. I would like you to see right off the bat that there is no squared trigonometry in there. What that means is right now, there are no Pythagorean identities that I can work with. You're not allowed to just square the top and bottom of a fraction. That isn't the same thing. For example, 1/2, 1/2, you square the top and bottom, you get 1/4, no longer equal. Can you multiply the top and bottoms of fractions? Yes. Add? No. Square? No. Root? No. See, there are certain things we can do, but fractions, the only thing I could do to the top and bottom is multiply. No squared trig, that means no Pythagorean identities. What is the only thing we could do with these 2 triangles, these 2 fractions then? What do you mean simplify? There's no identities because there's no squared trig. So how could I possibly simplify right now since there is no squared trig? Common denominator. When you see 2 different fractions with trigonometry in them and there aren't any Pythagorean identities there for you to work with, most of the time you're going to be hunting for a common denominator and combining them to a single fraction to see what happens from there. Yes, sir? There's no equal signs. There is no quote unquote add it over. To what did you, let me ask you, what did you add it over to? There is no equal sign. You're not solving for anything. You're simply simplifying an expression. In order to find a common denominator, we're going to have to multiply some things, right? You can't add or subtract to the top and bottom of fractions, so the only way that you can ever change the bottom of a fraction is through multiplication of the top and bottom. 1 minus sine x and cosine x have absolutely nothing in common. And since they have nothing in common, the common denominator is going to require you to just simply multiply 1 minus sine x and cosine x. So that's where we'll begin. Multiply by cosine x on the top and bottom for the left one. And for this one, we'll multiply by 1 minus sine x on the top and bottom. Just like when we're working with rational functions, like we did in chapter 1, actually, I think, when you're trying to simplify things like this, you don't usually want to multiply out your denominator, because what you're hoping is that when you combine all of your numerators, something will factor and cancel. Strong suggestion, keep your denominators factored. I'm hoping that it's obvious that now we will have a common denominator of 1 minus sine x times cosine x. Because of that, I can write this as a single fraction. Here, I have cosine x times cosine x. I'm just showing a lot of work. This is a multiplication dot. Cosine x times cosine x, that gives us cosine squared x. Here, I will need to distribute. What am I distributing? Somebody whispered it. Negative sine x, not sine of x, negative sine of x. So distributing that negative sine x is going to give me a minus sine x, and then multiplying these two negatives will give me a plus sine x times sine x, which is sine squared x. There. Common denominator. Combine the numerators. What do you see? Someone's got to see it. Well, you don't count. You can't see anything. He's all the way in the back. He's always squinting. What do you got for me? There's a Pythagorean identity sitting on the numerator. But what? So what am I going to be looking at in that numerator specifically? Well, what's that? You're right. There's no plus or minus 1, but what do you see? Cosine squared x plus sine squared x equals 1. That is the Pythagorean identity. Cosine squared x plus sine squared x equals 1. The order of addition doesn't matter. I could rewrite this order, say cosine squared x plus sine squared x minus sine x. It doesn't matter because it's addition. So those two things do combine to give me a 1, boop, just like that. So nothing is canceled. It's just that cosine squared x plus sine squared x equals 1. The numerator then is 1 minus sine x. And our denominator happens to be, oh look, 1 minus sine x times cosine x. This 1 minus sine x, it needs to be treated as a single object. So this object down here cancels that object from the top. So this cancels this. What's left on top of the fraction then? There has to be a 1. The bottom is cosine x. Oh, and by the way, 1 divided by cosine x is secant x. That expression is equivalent to secant x. Very neat. Questions for me? What do we got? No questions? Yes, ma'am. A Pythagorean identity? Replace, yeah, so let's just say I see a tangent squared x plus 1. That's equal to secant squared x. Now, do we always replace? No, you would only do it if it's going to benefit you. You only do it if it's going to help you get closer to your goal. Since we were trying to simplify this thing as much as possible, then our goal was, well, can I replace and cancel? Starting in the next unit, well, not next section, we're going to be proving things are true. So it says, prove that this is true. So this is now our goal. So we'll be manipulating things to try to reach our goal. Oftentimes, there are identities that we don't use simply because they don't get us closer to our goal. But if it does, then yes, you replace. Yes, ma'am. So the purple is just the original statement. And the red is me making them have the same denominator. See, this one doesn't have a cosine x. This one doesn't have a 1 minus sine x. It's like if one of the denominators was a 3 and the other denominator was a 5, you'd have to multiply that 3 and that 5 because they have nothing in common. So this and this having nothing in common require me to simply multiply the two together to get a common denominator. Good? Okay. Any more questions? No? Okay. Well, we're going to be spending the rest of this section solving trig equations. We are going to find all the times where cosine cubed x divided by sine x equals cotangent x. Yes? Well, are you sure? Oh, okay. So the way it sits, not too helpful because this side of the equation is a fraction. Wouldn't it be nice if this side of the equation was also a fraction? Luckily, cotangent can be written as a fraction of two other trig functions. Cosine x over sine x. Look at that. You now have fraction equals fraction, and they have the same denominator. The only way these two fractions can be equal then is if the numerators are equal, right? I mean, the denominators already match. The only way these two fractions are equal is if the numerators are equal. That's the only way that this can work. How would we solve a question if it was written like this? Instead of writing trigonometry, I'm just going to use a random variable. How do we solve things like this in algebra? If you cube root, you're going to have m equals the cube root of m, so that you never divide by the object you are trying to solve for. Because when you divide by the object you are trying to solve for, you eliminate solutions. When you have variables on both sides of the equation, you have to bring it all to one side and factor. You bring it all to one side and you factor. Never divide by the object you are solving for, ever. It eliminates solutions. So the last thing we want to do here is divide by cosine x. No, what we want to do is subtract cosine x over to the left side. That'll give me cosine cubed x minus cosine x equals 0. Again, let's look here. You're going to have to factor this, so what do we see? Take out an m as a GCF, correct? For this one, it would be like this. Clearly, our m is standing in for cosine of x. We pull a cosine x to the front. It leaves behind a cosine squared x minus 1. Alarms should immediately start going off in your head because we have squared trigonometry followed by a 1. It's almost a Pythagorean identity. You don't have any that say cosine squared minus 1. But you do have one that says 1 minus cosine squared. So if we factor out a negative 1 again, like we did this yesterday, if we factor out a negative 1, that will change the order of that subtraction. And this is one of the 6 purple Pythagorean identities on the front of this page. 1 minus cosine squared x is equal to sine squared x. it is helpful to have these two memorized. They're very, very common. Is it a necessity? No. This one's a necessity, the blue one. But it's really helpful to know that those are both true because of this, simply through subtraction. So instead of saying 1 minus cosine squared x, oh, your question? Yes, what's up? Riley, what's up? Because so cosine divided by sine is cotangent, because tangent sine over cosine. Is that it? Oh, okay, cool. So instead of saying 1 minus cosine squared x, I'm going to say sine squared x. We have negative cosine x times, that's not subtraction, it's multiplication, times sine squared x equals 0. You now have a factored and simplified equation set equal to 0. The whole goal was to get it factored so we could set the factors equal to 0, right? Switch colors because fun. Yeah, let's go to orange. That means I have negative cosine x being equal to 0. I have to solve that. And I have sine squared x being equal to 0. I have to solve that. What do I do here first? What do I need to do? Yeah, multiply or divide both sides by -1. So we need to know when cosine of x is equal to 0. Well, let me remind you. Cosine is the adjacent side over the hypotenuse. The x coordinate, not this x over r. The only way on the unit circle where x divided by our radius of 1 can equal 0 is if x is 0. Where do I find x being equal to 0? The y-axis. Right here, I have a coordinate of 0, 1 with a radius of 1. So x over r there is 0 over 1. And right here, I have the coordinate 0, -1 with a radius of 1. So our x over r there is 0 over 1. At those two places, cosine of x is equal to 0. Where are those two places? Pi over 2. And then 3 pi over 2 because this is halfway between pi and 2 pi. 3 pi over 2. Great. Well, we're using radians because the domain was in radians. Yeah, so if it's asked in degrees, you can use degrees. If it's asked in radians, you need to answer in radians. It's a good question. Basically, you want to use radians. Radians are our friends. Angles that are done in degrees are yuck. We have these two answers for x. Yes, question for me? It's a variable that's standing in for an unknown angle. I could have said theta, but the question, it honestly was in the textbook, it's x's. It just means, hey, I don't know what this angle is. It's a variable angle, not sure what it is. How would you solve this? What would be the first thing you did? Root both sides. Take the square root of both sides, which would normally create a plus or minus situation, right? But the square root of 0 is just 0. Our job now would be to figure out when sine of x is equal to 0. We'll do it the same way. Sine uses y over r. The only way that you're going to get a value of 0 from the fraction y over r is if y is 0. Where do I have y values of 0? The x-axis this time. Here on my unit circle, this coordinate is 1, 0 with a radius of 1. So y over r is 0 over 1, which equals 0. And here, the coordinate is -1, 0, and again, radius of 1. So our y over r once again gives us 0 over 1. We cannot include 2 pi because it doesn't have a bracket on it. See, it's parentheses. So our two answers then in the first 2 pi are x equals 0 and x equals pi. So it would appear as though we have 4 answers. But I'm going to go ahead and tell you, there's only 2 answers. But why? Yeah, we found some extraneous solutions. Which ones are they? It is pi and 0, but why? Because sine is on the bottom. Because sine is on the bottom, sine of x is not allowed to equal 0. If you had realized that earlier, you could have avoided all of this work, because this here is a big, big no-no, because you cannot divide by 0. So none of this should have happened. The reason why extraneous solutions showed up is because right there, I disregarded the things that were creating problems, the sine of x in the denominator. Your only 2 answers are pi over 2 and 3 pi over 2. Cool? There is a lot of stuff going on. There really is. Okay, well, in the next one, there's no extraneous solutions. Once again, though, we are going to solve for x. It does say find all solutions. The first thing we're going to do is find the solutions in the first 2 pi, like we did in the last question. And then I'll explain to you what it means to say find all solutions. I'm going to make your life easy for a moment, and I'm going to say, why don't we say that m equals sine of x. I do believe that this will make this an easier thing to handle if we do it this way. If we replace all of our sine of x's with m's, we get 2m squared plus m equals 1. How would we solve this equation? We're going to need to factor, but what do we need to do before we factor? Well, if we divide by 2, I'll have a fraction here and here. Subtract 1. Remember, you cannot solve by factoring until it equals 0. So the first thing you need to do is subtract 1 from both sides. Good old Lizzie method, because there's a number in front of my leading squared variable. I need 2 numbers that will multiply to a times c. My a times c is 2 times -1 is -2. And I need whatever those 2 numbers are to add to my b value of +1. That one's very easy. The 2 numbers that multiply to -2 and add to 1, 2 and -1. Awesome. The only quote-unquote difficult part of the Lizzie method is remembering to divide by a. Your a value is 2. M plus 2 over m minus 1 over. Your a value is 2. We can see the solutions for m. What does m equal here? -1. And what does m equal here? 1/2. Don't we feel accomplished? Woot, we solved for m. Unfortunately, the question didn't say to solve for m. It said to solve for x. And remember, m stands for sine of x. We now know then that sine of x has to equal -1 and sine of x has to equal +1/2. Remember, sine is y over r. The only way that I could get a -1 is if my y value and my r value are equivalent, but one of them is negative. Oh, by the way, radius can't be negative. I guess that means y must be negative. That happens y over r there is negative 1 over 1 at 3 pi over 2. Now sine of x equaling 1/2 has more than one answer because sine is positive in more than one quadrant. Which two quadrants can I find positive sine values? 1 and 2, because I needed positive y values. So quadrants 1 and 2. In order for sine to be 1/2, I need my y over r to be 1 over 2 y r, which would force this to be a root 3 and this to be a negative root 3. And I am dealing with a special right triangle. What size reference angle can be found across from a 1? 30 degrees. In radians, that 30 degrees would be pi over 6. And since this is also going to be a 30-degree reference angle, this is a pi over 6 before pi, 5 pi over 6. And those are your three solutions in the first 2 pi. The question does say to find all of the solutions though. That means for all infinity. Remember, trig functions go on and on and on, 2, 4, 6, 8, 10, 12 pies. It doesn't matter, I could keep going around and around and around. So how do we do that? Just remember that every time you turn a full circle, you're at a coterminal angle. It's the same as doing nothing, right? A full circle is 2 pi. These are the three answers in the first 2 pi, but if you're trying to identify all of the answers, you have to write it like this. This angle plus a multiple of 2 pi. And that multiple better be a whole number, right? So you say where n is an element of the integers. The integers are non-decimals. They're non-decimals. Think about it. -1, -2, -3, -4, 0, 1, 2, 3, 4, 5. You multiply any of those things by 2 pi, and you have just told me a number of full circles. And turning any number of full circles is the same as doing nothing. This means the letter n stands for any number with no decimals. N is an element of the integers. That's how you write it as all solutions. And then you do it for the other two as well. That's what it'll look like in the back of your textbook. What's so difficult about that? What English? That means element of. It's not English, that's a math symbol. If you have to say all solutions, you do plus 2 pi n. Where, yeah, because this says some number of full circles. That's all that says. Because if you don't say n, you're just saying 2 pi. That implies only. Because if you don't say that n is an integer, then that means n could be a decimal. But 0.5 whole circles will not land you in the same spot. It must be a whole number of full circles. N is an integer. Yep. And lastly, this question is involved. Stay with me on this trip, okay? I haven't written in enough ink today, so let's use pink. How would you start solving for theta? What would be the first thing you would do algebraically? Just like standard algebra, folks. You subtract root 2 to the other side. Come on, you guys are killing me. If this had said 2x plus root 2, solve for x, okay? First thing you do is subtract root 2. Then, what's next? Dividing by 2. Root 2 over 2 is a special fraction. It happens to be the rationalized version of 1 over root 2. It's what you get if you rationalize that denominator. Yes? Well, this is a fraction of side lengths, which means we could figure out at what angle that's occurring. Yeah, and we will need to do that. However, here's the problem. It doesn't say cosine of theta. It says cosine of 3 theta. No. Yes? Well, because here's what it says. We need to figure out where this happens. What it says is cosine of some angle gives me this ratio. And where is cosine negative? Okay. Yeah, 2 and 3, the left side, yes. Quadrants 2 and 3. That's where I can find cosine being negative. Tell you what we're going to do. Let us say that x equals 3 theta. If I say x equals 3 theta, I have cosine of x equals negative 1 over root 2, and I can easily figure out the answer for x in quadrant 2 and the answer for x in quadrant 3, can't I? Here we have side lengths of negative 1, positive 1, negative 1, and then root 2's. Now, Liam, this is what you were talking about. What kind of reference angle am I going to find inside this triangle? Liam, a 45-degree reference angle. Now, 45-degree angles, since we are trying to figure out what these are in radians, a 45-degree angle is what kind of radian angle? It's a pi over 4, but this one happens to be a pi over 4 before pi, so it would be 3 pi over 4. And this one happens to be a pi over 4 after pi, 5 pi over 4. And you're thinking, man, that was easy peasy. Well, yeah, if I was solving for x, that would be easy peasy. But I'm not solving for x. I'm solving for theta. The problem is our domain originally was this. That's the original domain. These two are the same thing, right? But we're not working with theta, we're working with 3 theta. So what I need to do is I want to change my domain so it doesn't say theta here, instead it says 3 theta. So I just multiply this by 3. But if I multiply one part of an equation by 3, got to multiply all of it by 3. And oh, by the way, 3 theta is x. So the x values that I'm solving for are not from 0 to 2 pi. Well, the x values I'm solving for are from 0 to 6 pi. Why? Because this thing will complete 3 full cycles in 2 pi. So if you're trying to solve for x, you ready for this? 0, 2 pi, 4 pi, 6 pi. And every time it hits the ray, that is a solution. We found this one and this one, but we add 2 pi to each of them 2 more times. 2 more here and 2 more here. And please remember, we are talking with over 4s, so 2 pi is 8 pi over 4. So we take our x values and we say, okay, x equals, no, it's a mistake. So x equals 3 pi over 4 and then 5 pi over 4. Then we hit this one. So we add 2 pi to that, because adding 2 pi lands in the same place, which is going to give me 11 pi over 4. Then we hit this one by adding 2 pi to that, 13 pi over 4. I ran out of horizontal space, so unfortunately I will have to come down here. Then we hit this one, which is 2 pi after that, 19 pi over 4. And then lastly, this one, which is 2 pi more than that, 21 pi over 4. We're not done, don't back up. Those are the answers for x. Your job was to solve for theta. Remember, please, that x was 3 theta. So how do we solve for theta? We divide by 3. You multiply all the denominators by 3, and you have solved for theta. Theta is 3 pi over 12, 5 pi over 12, 11 pi over 12, 13 pi over 12, 19 pi over 12, and lastly, 21 pi over 12, which, by the way, is less than 2 pi. We stayed inside our domain. That is all 6 answers for theta. Sheesh.